Welcome back to the Explainer. So, if you remember our earlier chats, dry-type transformers, like the Reezy block, rely on a solid resin cast coil just sitting in open air. Great for simplicity, right? But they definitely have their limits. Today, we're flipping the script and looking at the alternative, liquid immersed transformers. We're going to break down how they operate by mastering three very specific design axes: winding configuration, insulation fluid, and classification society approvals. Let's just dive right in.
Okay, so here is the big unlock. By explicitly choosing to submerge the windings in an insulating fluid instead of, casting them in solid resin, you open the door to entirely new electrical configurations. Things that standard dry types simply can't pull off. Yes, you get a highly robust fluid-cooled unit, which is great, but the absolute most critical capability this physical change unlocks, it's the ability to easily build multi-winding transformers.
Now you might be wondering, why do we even want multiple windings in the first place? Well, this connects right back to our foundational discussions on grid-side performance. A standard diode rectifier draws current in these jagged, non-sinusoidal pulses, and that generates harmful harmonic frequencies that basically circulate through your ship's entire electrical network. Not good. But by submerging the windings, engineers can actually build multi-winding setups with phase-shifted secondaries. These phase shifts actively cancel out specific harmonic orders right at the source, literally before they ever have a chance to hit your rig's switchboard.
So looking at our first design axis, the windings, we can use a pretty simple visual rhythm to see how this scales up. A basic 2-winding transformer feeds a standard 6-pulse rectifier. Step that up to a 3-winding transformer, which has 2 secondaries phase-shifted from each other, and boom, you can feed a 12-pulse rectifier. That harmonic cancellation starts happening just through that phase shift alone. Take it all the way up to a 5-winding transformer, and now you're feeding a massive 24-pulse rectifier. And the real-world impact of this proportional scaling, it is massive. By adding more phase-shifted secondaries, you actively cancel more harmonic orders. When you upgrade from a 6-pulse system, which has heavy aggressive distortion, all the way up to a 24-pulse system with 4 phase-shifted secondaries, you drastically reduce the distortion on your rig's network. You're getting the cleanest possible current draw, which means you minimize the need for heavy, super expensive harmonic filtering equipment downstream.
All right. Let's move to the second design axis, the insulation liquid itself. This is a stark, real-world engineering trade-off between maximizing fire safety and, managing your budget. First up is Midal. It's a synthetic ester that gives you a high fire point and biodegradability. This one is highly popular when you really don't want to have to explain an environmental disaster to your boss. Then there's silicone fluid, which offers strong thermal and oxidation stability. And finally, you have mineral oil. It's the traditional option, and yeah, it's the cheapest, but you definitely get what you pay for because it comes with the lowest fire point of the 3.
Our third design axis is a bit of a harsh regulatory reality check. You absolutely must adhere strictly to the classification society approvals that govern your specific offshore rig, whether that's DNV, ABS, or Lloyd's Register. But whatever you do, please do not make the mistake of treating these class approvals as just mere administrative paperwork to be checked off at the very end of a project.
Because that class approval literally shapes the physical asset from the ground up. I mean it. If you wait until the end of the line to check these requirements, you're going to find yourself completely re-engineering the transformer after the fact. The governing class society dictates everything. Can you use a corrugated tank, or do you need a radiator tank? Must the unit be hermetically sealed? What are your allowable cooling systems, natural air or forced water? And what about the strict parameters for hazardous area Zone 2 classifications? If you specify any of this wrong, your transformer simply won't be allowed on the rig. Period.
Okay, before we wrap this up, let's do a quick check and test your mental map of what we've covered today. Think back to those multi-pulse rectifier designs we mapped out earlier. If you are the engineer responsible for ensuring the absolute cleanest harmonic performance, the minimum interference on your vessel's grid, which transformer configuration are you writing into the spec?
Got your answer? To get the cleanest possible harmonic performance on your single-line diagram, you've got to specify the 5-winding configuration feeding a 24-pulse rectifier system. Why? Because more phase-shifted secondaries means more harmonic orders get canceled out before they ever reach the switchboard. It is absolutely the ultimate solution for inherent, built-in harmonic mitigation.
So, before this explainer, liquid immersed transformers might have just been, a generic gray box on a diagram to you. But now you know the 3 real design axes. You've got winding configurations setting your harmonic performance from 6-pulse up to 24-pulse.
You've got insulation fluids trading off fire safety against cost, and you've got class society approvals constraining the entire physical build from day one. Now that you've mastered these levers, our next explainer is going to cover the final major vendor category in rig drive systems, which is braking resistors.
Because every drive system eventually has to dump braking energy somewhere. And as we prepare to look into atmospheric tanks, sealed pressure tanks, and titanium-encapsulated resistor elements, I want to leave you with this provocative thought. When a massive drawworks lowers a 10-ton load and the motor generates instead of consumes, exactly where does all that intense, potentially explosive braking energy actually go? And more importantly, how do you manage it without starting a fire in a cramped, sealed offshore machinery space? We'll unpack exactly how that's achieved in our next deep dive.